Hi, my name is Rosalind Carson, and I'm going to talk to you about my favorite perspective on teaching trigonometry, and it is not with the trig ratios. I'm going to call them trig equations, even though trig ratios are equations. I do not teach them in that traditional sense. It's like a whole new perspective. It's like looking at art from a different angle, so you can analyze it from a whole different viewpoint. That's what we're going to do. And this is a very historical look at trigonometry. It's the way it was created, and I'm going to show you how this new perspective of teaching trig equations makes the calculations much easier for the students. Okay, so when I refer to trig ratios, this is what I mean. The traditional sine is opposite over hypotenuse, cosine is adjacent over hypotenuse. It's only related to right angle triangles. You know what? If I get your students first before they ever are introduced to trigonometry, they won't see these. They'll see it after because it's in textbooks and whatever, but they'll understand it more and they can turn it back into a new perspective, which I'm going to show you. All right, we're starting with Hipparchus. Hipparchus is the father of trigonometry. You read history of math books, he's deemed as the king of trigonometry. Why? Because he's the first person who started recording, like mapping star location for navigation using circles and whole chord lengths, because as the star travels along like a semicircle path through the sky, so it's like taking a cross section of the sphere, right? So they can imagine the sky as a sphere, like a dome. You take a cross section as the star is traveling across. What he noticed was if he drew in the chord length to that horizon, that chord length would change in length as the star was moving. So he was using the chord length calculations to note where the star is located at a certain point in time, right? So his table of chord values were so popular that they were then learned by Ptolemy, that they were then learned by the Indian scholars, that were then learned by the Arabic scholars, that were then put into Ptolemy's amalgamous books. Like, this is the guy, this is where it was generated. So we're going to do it like Hipparchus. He used whole chord lengths, so are we. And I'm going to show you how this makes the calculations so much easier. So we're going to draw in the chord length at that star position. So your stars traveled up from the horizon in the east. James Tanton gave you all that history of how the star travels through the sky, why our quadrants are quadrant 1, 2, 3, 4, and where they're located. And the easiest amount of degrees travel to start with usually is 45 degrees. So let's just say that angle theta there is 45 degrees. And I'm going to draw on the whole chord length. And now I'm going to complete the triangle that would be created from that whole chord length and the center of the circle. So I drew the chord as a yellow line there, and I know the angle of movement was 45 degrees from the horizon. Now in my circle, I'm using one thing that's different than Hipparchus. He used a radius of base 60, so it was 60 units long. So did Ptolemy. Actually, wasn't until a lot later that they changed it to base 10. We use base 10, so we use a unit length of 1 for our radius. They use 60 because it was easier for mental math. That's a whole other lecture. So yay for you, we get to use base 10. All right, so I'm going to pull this triangle out of the circle so you can take a look at it. Students have enough information right here, right now, to calculate the whole chord length. So if you want to pause and see if you can figure it out, go for it. You can have a whole conversation with your students about how are you going to know what angles do you know in this new triangle? Well, we actually know that angle's 90 degrees. Why? Well, you can go through all the math about how those are two congruent triangles put together. You have that conversation. We know two legs of that blue triangle are 1 because they're both radiuses of the circle. It's a right angle triangle. We could use Pythagorean theorem to find the whole chord. It's root 2. Cool. All right, so this is the first beautiful point of using whole chord lengths. If I want to find the half chord length, I just divide that by 2. There are no radicals in the denominator. Yay, we don't have to rationalize the denominator. So if you're introducing trig before this happens in your math curriculums, this is the problem in some provinces or states. Sometimes trig comes before rationalizing denominators. Sometimes it comes afterwards. Do you have to rationalize denominators? Well, if you do it the way Hipparchus invented it, it's not a problem because there's no radicals in the denominator and I get an exact length. Okay, I drew the half chord length as green so it would pop out. James gave you the history of why our Latin translation for the word sine really goes back to the Indian Sanskrit word half string, half chord, and it really was half string first because you can imagine like a bow and arrow in that picture. If you can use your imagination, the arc of the circle is the bow and the arrow is the diameter. Anyways, lots of fun visuals there, but the half chord length after traveling 45 degrees, we now call sine after traveling 45 degrees, but sine means half chord length. And that's just root 2 over 2. Nice, easy calculation. It's an exact value. The students can see it. They can see the geometric measurement, which is way more powerful than going sine 45 and you get this long decimal. What does that long decimal measure? And they have a hard time visualizing that as a length. When you do it with geometry and it's hands-on and they draw it and they can touch it, now they can see it. It makes more sense to them. The other measurement we're going to do is the distance from the center. So where's that chord located? That chord is a certain distance from the center. That's another measurement that keeps changing as the star is moving. That is interesting to use in our calculations. So because it was so interesting, we had to denote it as cosine, which is the distance from the center. And if you look in that triangle that now has the red line for cosine, the distance of the chord to the center, and that green line for half chord length, we get an isosceles triangle. The other angle has to be 45 degrees because angles in a triangle add up to 180. Great, isosceles. So now we know sine 45 degrees is the same as cosine 45 degrees. They're both going to be root 2 over 2. And now we have a nice physical diagram showing the students why cosine at 45 degrees is the same length as sine at 45 degrees. It's an isosceles triangle. All right. We're going to travel around the circle in increments of 45 degrees, getting the exact length measurements, so exact lengths, not decimal approximations, exact length measurements for the half chord lengths and the distance from the center. And you can have the conversation about why some of them are positive and some of them are negative for orientation purposes, but it's very straightforward for the students. If I travel 90 degrees, that whole chord length that's perpendicular to the diameter is 2. So of course, half of it is 1. So sine of 90 degrees is 1. Put it in your calculator. Voila, it's 1. Yay. And cosine is the distance of that chord from the center. Well, wait a minute. The chord goes through the center, so the distance is 0. So pretty easy calculations. The next easy one is traveling by increments of 30 degrees. Okay, so draw on the whole chord length the way Hipparchus did. Here's my whole chord that's perpendicular to the diameter. I'm going to complete the triangle. I'm going to pull the triangle out. Get your students to calculate the whole chord. They have enough information in that diagram right there to calculate the whole chord length just like Hipparchus did. Pull it out, put in some information that you know. 2 legs are equal to 1 because they're both radiuses of the circle. The angle in between those 2 legs is 60 degrees. Wow, we are going to have an equilateral triangle, so that chord length has to be 1. Wow, is that ever nice? Because now all I have to do is divide that by 2 to get sine. So half chord length after traveling 30 degrees, 1/2. That, our Latin translation, sine after traveling 30 degrees is 1/2. All right, so I put that in green so you can see the half chord length after traveling 30 degrees is 1/2. Now the distance from the center, there it is in red. You can use Pythagorean theorem to calculate it. The lovely thing is there's no radicals in the denominator. Yay! And again, you can travel around the circle in increments of 30 degrees, fill in your chart of all these exact values. Now, some students take a little longer to do all the calculations. I think it's really important for them to do this work themselves and draw their triangles and draw their whole chords. And while other students are finished way ahead, I get them to start plotting these on graphs. Okay, I'm very curious to know, well, what kind of graph would be created if I graph all of those half chord lengths as a function of the degree movement. So on my x-axis, I'm going to have my degrees, and on my y-axis, I'm going to have all the half chord lengths. Let's see what happens. And then do a separate graph for the distance from the center, the cosine, and see what you get. So you have some students graphing, some filling in the chart. Everyone's working, everyone's learning some physical representation of what these trig equations are creating as functions. Very cool pictures. And when students figure out the visual themselves, it's meaningful. The last one we have to talk about is the tangent. Okay, everyone knows tangent's opposite over hypotenuse. Well, if you haven't taken that introductory trig class, you don't know it, but they've heard the word tangent. Latin meaning for tangent means it touches at exactly one point. Now, if we go further back into history, the Europeans learned a lot of their mathematics from the Arabian mathematicians. And the Arabians use another word for tangent, and that other word is shadow or shade, which is another word, like their word for shadow or shade can also be used for tangent. And when I worked with a bunch of math teachers who spoke Arabic, they said, well, that is how we discuss it at first, right? Because if I draw my tangent line to the circle at the horizon, now tangent lines can go up and down forever, right? What I'm interested in is a specific tangent line segment, but how do I know how long that tangent line segment is going to be? Well, it's the shadow cast onto that tangent line, creating a line segment that's kind of like a shadow or a shade or my vision of perspective from that angle of movement. So if you look at angle alpha there, and if I'm looking out, my perspective has a certain window of perspective or a shadow, and that's the tangent line segment I want to calculate. Interesting, hey? All right, so I'm going to pull out my original triangle with radius 1, that's the hypotenuse 1. Opposite side's going to be sine theta, the half chord length, and the distance from center is cosine. Now I want to look at that triangle where one of the legs is that tangent line segment created by that shadow. And I pull it out. Now it also has that angle alpha there, and it also has 90 degrees. So I have similar triangles. And they both have 90 degrees because they were drawn perpendicular to the horizon. And I know that bottom leg is equal to 1 because it's also a radii of the circle. Now the cool thing here is we're going to use Thales math. Thales was the first recorded mathematician in history that we have in records where a specific person's name is mentioned. Thales. Looks like Thales, but it's pronounced Thales. And he wrote down some really interesting math called similar triangles. And, you know, we just take it for granted. Oh, similar triangles, that's so easy. But like this was mind-blowing back then because he could start to measure things that he couldn't touch, like the height of a pyramid, using similar triangles. So this was like the beginning of abstract thought. So really important in the history of math. Right here, right now, we're going to use similar triangles. Okay, so what do we know about similar triangles? They have to have corresponding angles equal. Yep, those two triangles are going to have corresponding angles equal. And now what that means is one triangle is just like a scale factor bigger or smaller of the other one, right? It's just like pulling one and making it bigger or smaller. So all I have, like, then I know that the sides are like scale factors of each other. So no matter how the students set up the sides as proportions of each other, right? Because one has to be the same, you know, scale factor, bigger or smaller than the other one. However they set up their ratios, they're going to get tan is equal to sine over cosine. So you might say tan divided by sine would be the same factor as 1 divided by cosine. They might say sine divided by cosine is the same as tan divided by 1. However they want to set it up, rearrange the equations, tan will turn out to be sine divided by cosine. So right away in introductory trig, we start talking about how tan, that tangent line segment, is equal to that half chord length divided by the distance from the center, sine over cosine. And it doesn't matter how big the triangle is. So this is really interesting, but I want them to have that visual. Another trig identity that just pops out all the time is the Pythagorean identity. And I'm just throwing that in there because it's so obvious from right triangles that we would use Pythagorean theorem, and there it is. And I'm going to do another video showing how this new perspective on trig is going to make trig identities a lot easier for your students. So stay tuned for that one. Okay, so we know all the exact values for sine and cosine when the radius is equal to 1. And the students know exactly what these root 2 over 2s and these root 3 over 2s look like. So it's not just these random decimals that give them no meaning or no concept of size, right? So now they know a root 3 over 2 is longer than a root 2 over 2. Even that kind of visual concept of radical lengths is important. Now what happens when I'm going to start calculating side lengths in right triangles where the hypotenuse is not equal to 1? Let's draw one. If it's a right triangle, it's going to be some kind of scale factor of one of the triangles we already know. It's either bigger or smaller. So whether it's bigger or smaller, the hypotenuse is now a new length. So I'm going to call it h. It's just not equal to 1 anymore. Now I can label the other sides in that triangle. I always know the opposite side is sine. So I start interchanging those words. When I'm looking at that angle alpha, I'm finding the half chord length. That's the opposite side to that angle in the triangle. So I start interchanging the language because if they've already heard the words opposite and adjacent, I want them to know why they're used. And I also want them to know that language because after they've taken trig for me and they go do textbook questions and they're seeing this opposite or adjacent, or the test question says find the opposite side, they need to know what we're talking about. So if I want to label that opposite side, I know it's sine of alpha, but now it's a scale factor. It's bigger or smaller by the size of the hypotenuse, by a scale factor of the hypotenuse. So I just have to multiply sine by h, hypotenuse. And if I want to find the adjacent side, I just go hypotenuse times cosine because that's all it is. They're just scale factors of each other. So this is the new perspective. These are the trig equations I'm going to use now all the way into advanced trigonometry. And I want to show you how this perspective, looking at the equations written like this, not like the original trig ratios, like this, is going to make the rest of our trig calculations and trig identities easier for the students to calculate, easier for us to visualize. All right, so if students have seen the trig ratios before coming to me, we'll say, look, this is like art class or English literature. It's really good to take a look at something from a different perspective. This is what we're doing. So really, this is just a rearranged form of the equation from trig ratios. But now instead of using the trig ratios, I'm always going to say, if I want to find the opposite side, it's hypotenuse times sine. If I want to find the adjacent side, it's hypotenuse times cosine. This is what I'm using. All right. So if I want to label the sides in a triangle where the hypotenuse is 13, boom, opposite side, 13 times cosine 30. Hey, I don't even need a calculator. I know exactly what that is. Sine of 30 is 1/2. So that length is just 13 times 1/2. No problem. The adjacent side is cosine 30. I know that length too, and I'm just going to multiply it by 13. And I have the exact values right there without a calculator. I don't even need a calculator. And now I'm getting exact values for known angle movements that we calculated previously. All right, let's have a triangle where I have to find a missing side. Classic introductory trig question. Given a triangle with angle 71, and it's the right triangle, the side between 71 degrees and 90 degrees is 140 meters. That's the adjacent side to the angle 71 degrees. We don't know the length of the hypotenuse. Please find h. Okay. Well, I know that 140 is the adjacent side, so I'm going to actually write that. How do I find the adjacent side? It's hypotenuse times cosine. Okay, so now I know 140 is equal to hypotenuse times cosine. Cosine 71 is the distance from the center of the circle to the chord after I've traveled 71 degrees. It's an exact length. It's a number. It's a length in the circle on the diameter. Like it's just a length. It's a number. So cosine 71 is an exact distance. It's a number. I can just divide both sides of the equation by that number. I have hypotenuse. And for those who have taught intro trig to some really weak students, we know an unknown in the denominator is a stumbling block. We've eliminated that. When you are always using the trig equations from this perspective, opposite equals hypotenuse times sine, adjacent equals hypotenuse times cosine, there's no unknown in the denominator. Give it a go. Take any of those intro trig questions where you're like, find the hypotenuse, find this missing side, find this side. No unknown in the denominator. If I want to find the other side and I know the hypotenuse, I know the opposite side is hypotenuse times sine of 71. It's just numbers that I already know. No problem. Last one I'm going to address in my intro trig is tan. We introduced it as sine over cosine, but they're going to see it in the textbook as opposite over adjacent. So I just address it right away. Guys, I don't want to change your perspective of tan from intro trig to grade 12 trig where all of a sudden we're doing trig identities and now I have to tell you tan is sine over cos. No, we see tan as sine over cos right away. So why does the book use opposite over adjacent? Well, guys, we know what the opposite side is. It's hypotenuse times sine. Do you know what the adjacent side is? Yes, it's just hypotenuse times cosine. Hypotenuse divided by hypotenuse is 1. We're just left with sine divided by cosine. So tan is sine divided by cosine, no matter what size the hypotenuse is. So that shortcut version of opposite over adjacent, what they're really saying is that it's sine over cos. So instead of changing students' perspective from one grade to the next, we just keep it the same. It's always going to be sine divided by cosine. Sine is the opposite side times hypotenuse. Cosine is the adjacent side times hypotenuse. So we're all good. All right. I think that's the end of my show, but we are going to do some more with trig identities using this new perspective. So stay tuned. Bye.